Well, good afternoon, it's Charlie ZL2CTM. Well, the RF antenna amplifier is built, so I just want to spend this video looking at the design behind the amplifier and then looking at some tests, throwing in some signals and looking at the output. So that's the aim of today's video. So, switching through, what I wanted to do just in terms of design goals for this particular amplifier, I want around 10 dB gain. That was a design goal. I don't want too much more than that for the antenna RF amplifier, just in order to preserve the noise figure for the overall radio. I want it to be reasonably broadband, so I'm going to utilize some feedback. Just gives me a little bit more flexibility down track to use the amplifier on other bands. In an effort to reduce overloading for really strong signals coming into this particular amplifier, I'm going to have a little bit more current passing through it. I want to have the input and output to be roughly 50 ohms to match downstream and upstream circuits, and we'll have a good liberal use of rules of thumb. So that's the configuration we'll be looking at. It's going to be based on a 2N3904, just a nice stock standard transistor for this particular situation here. It's going to be in a common emitter configuration with voltage divider biasing. Going to employ, like I say, some feedback to give it a bit more broadband. So we're going to have some feedback coming from the collector back to the base, as well as some degenerative resistance here in the emitter circuit. So just before moving on, we've got a 100 ohm resistor here to help decoupling from the overall VCC, and on the circuit side we've got a 100 nanofarad capacitor and our 100 microfarad capacitor there. What else? Couple of DC blocking capacitors there. Again, 100 nanofarad capacitors just to not upset our DC biasing for that feedback circuit. So let's divide this into two things. Well, first we'll look at the DC biasing, and then we'll look at working out the value of RF and RDGen. So this is a 3904. I'm going to set the quiescent current through the device at 20 milliamps, and if we go to the spec sheet at 20 milliamps, we can extrapolate and we can work out that our minimum beta is going to be around 80. Our maximum is going to be 300, which gives us our geometric mean of 154. So in terms of working out RE, we're going to set the emitter voltage there to be a 10th VCC, so 1/10 of 13.8 equals 1.38 volts. So from Ohm's law, the voltage across it divided by the current through it gives us resistance. So 1.38 volts divided by 20 milliamps flowing through it gives us 69, so we'll use 68 ohms as a standard value for that one. R2, this one here, again we'll look at the voltage across it and the current through it. You'll recall, in order to get a nice stiff voltage divider biasing network here, we want to have at least 10 times the base current flowing through these two resistors here. So we'll have 10 times passing through here, and when it gets to this point we'll have another IB being added to it, so there'll be 11 times the base current flowing through R1. So right, so the voltage at the base is going to be the voltage at the emitter plus an additional 0.7 volts, which comes out at 2.08. We know that our base current is going to be our collector current, which is close enough to our emitter current divided by beta. So 20 milliamps divided by 154 gives us 130 microamps. So now that we have that, we can go 2.08 volts at this point divided by 10 times the base current comes out at 1600 ohms or 1.8 k ohms. So that's what we use for R2. R1, again we'll look at the voltage across that device, which will be the voltage, so it'll be 13.8 volts minus 20 milliamps times 100 ohms because the voltage drop there, so that's what's there, and this point here we already know is 2.08 volts. So we can work that out now. So 13.8 minus 20 milliamps times 100 ohms minus 2.08 volts, which is the voltage here, gives us the voltage across that device. So that voltage divided by 11 times our base current comes out 6797 ohms, or we'll just use 6.8 k ohms as our standard value. And just quickly looking at power dissipation of the resistors, make sure we're not going to burn anything out. Our main concern is the 100 ohms and the 68 ohm resistors in the main part of the current flow. 100 ohms is greater than 68, so we'll just look at this one. If this one's good, then that one's going to be good as well. So we know power equals I squared R, so 20 milliamps squared times 100 ohms equals 40 milliwatts. These are quarter watt resistors, so we're good there. We're well under our max power dissipation for that 100 ohm resistor. In terms of our coupling capacitor coming in on the base circuit, we know that our capacitive reactance equals 1 over 2 pi Fc. So we'll just notionally go with the good standard 100 nanofarads and see what that works out to be. So 2 pi times 7.1 megahertz times 100 nanofarads, all under 1, comes out at 0.22 ohms. So that's good. So a couple of rules of thumb there. It's well under 100 ohms, so we're not going to get too many losses across it. And it's also less than 1/10 of Rn. So that's good. Right, so next steps, now that we've worked out our biasing resistors, is to work out the two feedback resistors, so RF and our RD-gen. So a couple of rules of thumb there. So interesting, when RF times RE, big RE that is, equals RS times RL, then our input resistance is approximately equal to our source resistance, and our output resistance is approximately equal to our load resistance. So where RF is, as we saw before, is that resistor between the collector and the base. Big RE equals a little re plus our RD-gen, and we know that our little re equals 26 divided by IE in milliamps. And RS is our source resistance. So if I just nip back to here, so RS equals 50. Now what I will say here, RL is the resistance seen in the collector, which is going to be here. Now that's going to be 200. I think I mentioned that before. So this transformer is going to transform 50 up to 200. So when we go back to this rule of thumb over here, when we see RL, it's going to equal our collector load resistance, or in this case, like I say, equals 200 ohms. Also, gain is approximately equal to 10 log RL, that 200 ohm resistor, divided by big RE, which we saw up here was little re plus RD-gen. So armed with these formulas here, we can start to work out what our unknowns are, and then substitute back into various formulas to work out our various resistors. So let's start off by looking at RD-gen. That's the one in the emitter circuit. So first things first, in order to find RD-gen, we're going to use this formula here. We want to find big RE and little re, and therefore we can work that out. So using this one here, we can say that 10 dB, which is our desired gain for this amplifier, is approximately equal to 10 log RL divided by big RE. So 200 ohms divided by our big RE. So this is the unknown. So now we're going to rearrange this formula here to make big RE the subject, and that works out to be 200 divided by 10 raised to 10 BV divided by 10, comes out to be 20 ohms. So now we know that 20 ohms. Let's work out little re. So 26 divided by IE in milliamps. So 26 divided by 20 milliamps equals 1.3 ohms. So now we can use this one here. So therefore big RE equals little re plus RD-gen. So therefore RD-gen equals big RE 20 minus little re 1.3, which comes out to be 18.7 ohms. So we'll use 18 ohms. 18 ohms is going to be the value we're going to start off using for RD-gen in that emitter circuit. Right, so next one we want to work out So what do we do there? So with RDGen, so next one we're going to look at is the RF. So that's our resistor between the collector and back to base. So again, from RF times RE equals RS times RL, we can then substitute in our known values and make the unknown the subject. So we know what RE is, we worked it out before to be 20. We know what our source resistance is, it's 50 ohms, and we know what RL is, it's 200 ohms. So we can make RF the subject, so 50 times 200 divided by 20 comes out to be 500 ohms. So we'll use 470 as a standard value. So now we've got both our RF and our RDGen, so we're good to go there. Right, so we mentioned before that we're going to use a transformer to transform that 200 ohms, say again, to transform our 50 ohms downstream back into 200 ohms to be presented to the collector circuit there. So that transformer, going to use an FT37-43, nice broadband toroid there. So that gives us a turns ratio of square root 200 divided by 50 ohms, or an N equals 2. Another rule of thumb, we want the smallest winding at our lowest operating frequency to be roughly 4 to 5 times the resistance that is attached to that particular winding. So we'll have a look at that in a sec. So one option that meets our criteria of N equals 2 is a 12 to 6 turn transformer. This one here you recall potentially has been used many times on the 80 meter. So our smallest winding here, just looking at this rule here, is the 6 turn winding. If we go to an online calculator for the FT37-43, 6 turns works out to be 12.6 microhenries. And we know our inductive reactance equals, XL equals 2 pi FL, so we can substitute in. So 2 pi times 7.1 megahertz, our lowest frequency we're going to use, times 12.6 microhenries comes out at 562 ohms. Now that's the 6 turn one, and we said that's on the output side, so attached to that is the 50 ohms downstream circuit. So 562 divided by 50 gives us 11, so that's well and truly more than our 4 to 5 times. I'm going to try 8 to 4, so 8 divided by 4 still meets our criteria for N equals 2. Our smallest winding is the 4 turn winding. 4 turns with the online calculator comes out to be 5.6 microhenries. Again, using the same formula here, we can come out with 249 ohms. 249 ohms divided by 50 ohms equals 4.98. So that's good. So that's still meeting that. It's slightly smaller, so I think we'll run with that one. So that's one we're going to wind up and we'll put into the actual amplifier and test that one. Something else which I should have done back at the DC biasing stage, but I sort of tacked it on the end here, is just making sure we're not going to exceed our max power dissipation for the 3904. The 3904 allows you to have 625 milliwatts power dissipation. So we know power equals volts times current. We have V, we're going to set to be notionally VCE, and our current will be the current through it, so we'll use IE of 20 milliamps, which is close enough to IC. So again, the voltage across it, so 13.8 volts minus 100 ohms times 20 milliamps, so that's the voltage drop across that 100 ohm resistor in our collector circuit, minus, and I had a little mistake here, minus 1.38 volts. So you recall 1.38 volts is the voltage at the emitter. So collector voltage minus emitter voltage gives us VCE. And then multiply that with our current, 20 milliamps, comes out at 0.236 or 236 milliwatts. 236, as you can see, is well less than our maximum, well under our maximum allowable of 625, so big tick there. Rightio, so let's pause there and we'll have a look at the circuit itself, and we'll throw some signals in and we'll look at the output looking at the frequency response to see if we indeed have got a reasonably broadband, as well as what its gain is. Before doing so, we'll just have a look at the LTSpice plot, and then we'll look at the actual circuit itself. So back soon. So just taking a quick look at the LTSpice plot for the amplifier. Looks reasonably good in terms of being broadband. Our lowest frequency here is 1 meg, so I'm only really interested from 80 meters onwards, so around sort of here with 3 megs up to, and at the moment the right hand end there is 30 megs. So we can sort of see across that broad HF band there, reasonably flat, which is good. So quite happy with that. So quite different from that quite peaky response we get from an amplifier with no feedback, which makes sense. Our feedback giving us our broad nature, or broadbanding I should say. Rightio, so shifting through to a couple of checks on the board. So at the moment it's wired up, it's powered up, 13.8 volts coming in. It's got an input coming from the SIGGEN, currently set on 7 megs, and we've got the scope scoping the input as well as the output. The output there is a small 51 ohm resistor, and if you just very quickly just have a quick look at that, we can sort of see the various parts there. Coupling capacitor coming in, we've got R1 and R2, our DC blocking capacitor there with our RF from the collector back to the base, our emitter resistor there, again another DC blocking capacitor with our RDGen sitting there, and then our transformer there. On this side here 4 turns, and then on the collector side our 8 turns, with our 100 ohm resistor just up there. Again 51 ohm resistor just hanging on the we'll call it the secondary going this way of the transformer, to act as a load there. Right, so let's just have a look at the scope. So the scope is set up to be on the same settings for channel 1 and channel 2. So we're just looking at a direct comparison there between the input and the output. We said we're on 7 megahertz there, so if we were to work out what the gain is, it's going to be 20 log V out over V in, and because we've got the same settings, the vertical volts per division settings, we'll just go purely by a ratio. So just counting up, let's sure we're about, what's that, wrong one? 1, 2, 3, 4. Let's go with say 4 point, I'll go down to 4.1. So 4.1 divisions there. Our input is pretty close to 1 point, let's go with say 1.1 as well. So 1.1 divide, so 4.1 divided by 1.1, we'll take the log of that and then multiply that by 20, gives us 11 dB. So a little bit more than our 10, but certainly in the ballpark, so we'll live with that. So I'm just going to vary the frequency now. So we just said that's on 7 megs. Let's drop that down to say 3. And again, just looking at our V out here, so no great loss there at all. In fact, nothing. Let's come back up. 4, 5, that's 5, 6, 7, 8, 9, 10. So just starting to get a bit of a drop off there around sort of 14, so the 20 meter band. And then we're up now at 20. So to be honest, no, haven't lost a huge amount there compared. So, and I think fair to say pretty well in keeping, certainly at the high frequency end, in line with what was predicted. But significantly better, like I say, than having an amplifier with no feedback. So certainly a much broader. So yeah, that's up at 22 megs there. So let's come back down to 16. So really quite happy with that. So I think at this stage of the game I'm not going to try and do any more on trying to make that better. I think in terms of the overall gain that it's got, it's about right. The frequency response, certainly, bearing in mind this is going to be a 40 meter radio, is fine. Even if we were to convert it to 20 meters, I think the gain of this particular one is fine. Noting that in order to sort of preserve that noise figure, not after a huge amount of gain anyway, so I think that's fine. Again, as I mentioned it before, the amplifier, the audio amplifier is all configured and soldered up. Volume control there. The VFO's in place. That's the Arduino Nano, the SI5351, and that simple 16:2 display. I'm not too sure if there's a need to put a video up for this. If somebody wants it, or if there's a desire for it, please sing out and I'll make one up. It'll probably be just along the lines of the pins used, the interconnections, and then I'll throw the software up onto the blog. I've cleaned the software up a little bit and changed things subtly now. I've sort of gone with an approach where you can push down and rotate and get the various different tuning steps, and then that aligns over here. For the longest time I've had an underscore or a little line, but this approach here makes it a lot easier when you port this to a large LCD. So like I say, if somebody wants a video on that, then sing out and we'll look to do something. Otherwise, I'll knock it on the head there and say 73s, and I think the next part of this will be, so from a direct conversion point of view, will be the mixer. So we'll have a look at that ADE1, we'll get the output of the SI5351, that'll be at the incoming RF frequency, and then we'll put that in the audio amp and see how it goes, and then we'll move into a super hit. Anyway, I'm starting to ramble here, so I'll say 73s, and we'll continue playing around. Cheers all.